So today, what we're going to do is we do an important example through an app or an app. It's actually, we're going to do an example of of a specific type of application. So today we do, I guess I should be able to write appropriately. So what we're going to try to do is solve differential equations using power series. So if you think a few weeks ago, we solved a couple types of differential equations. And what we'd like to do today is we'd like to see how we can use power series to solve a differential equation. So here's the idea. So assume we'll have to sneeze. Hold on. I'm going to mute for a second. Okay, excuse me. I'm back. So here's what we want to do. Consider this equation. So consider y prime equals 6y plus 9 with, we had this initial condition. We want a specific solution that satisfies y of 0 equals 2. So we'd like to solve this equation. Now, we learned a few ways to solve this a few weeks ago. We could do this integrating factor, or we can get creative with maybe it's separable. So what we'd like to do today is we'd like to solve it using a different strategy. And here's the strategy. So let's quote unquote guess y is a power series. So what does that mean if y is a power series? Well, if y is a power series, that means it looks like this. It means y, which maybe it's a function of x or t, it doesn't matter. We'll use, I don't know, what letter? We'll use x. So that means y equals something like this. C sub 0 plus C sub 0, or excuse me, C sub 0, C sub 1 times x plus C sub 2 times x squared plus C sub 3 times x cubed. Now, we don't know what these coefficients are. All we're doing is guessing that the solution can be written as a power series. So this is just like a guess. Now, you might say, well, why did you center it at 0? And the reason I centered it at 0 is because I know information about my function y. I know that at 0, it's equal to 2. So I would, this suggests centering it at 0. The beautiful thing about a power series is we know immediately what its derivative looks like, because if I differentiate this, I get C1 plus 2 times C2x plus 3 times C3x squared. And what would be a good thing to do is to recognize that the derivative, say its kth term. What does its kth term look like? It has its first, its second, its kth one is k. times c sub k x to the k minus 1. So that's useful to notice. And by the way, what's the kth term of the function? The kth term is just c sub k x to the power k. We talked a little bit yesterday about this, how it's often useful to get an idea for what the general term of the series looks like. And so we now know what both of those looks like. Does anybody have a question about this so far? So again, we have a differential equation. We have this guy, y prime equals 6y plus 9. And we'd like to solve it. And our strategy for solving it is this new strategy, because we know what power series are now. We're going to guess that y is a power series. And what we're going to do is we're going to plug it in there and see what power series, if any, would work. So that's our game plan now. So let's do that. So here's the strategy. So if we assume y is a solution, let's write out what we have. We have y prime equals 6y plus 9. So that, by the way, let me double check something. Okay, so if we assume it's a solution, now let's plug everything in. Let's plug the left-hand side. Well, the left-hand side of this, we know what it is. From the previous page, it's C1 plus. So remember, if you go to the previous page, it's C1 plus 2C2 x squared. Or excuse me, 2C2x, and then it's plus 3C3x squared, etc. And then on the right-hand side, it's 6 times y. So it's 6 times C0 plus C1x plus C2x squared. And then this is plus 9. So again, all I did is replace y prime with what it actually is, and all I did is replace y with what it actually is, or at least what I think it is. Okay. What to do now? Well, one of the options we might have is we say, okay, there's a lot of stuff on the left-hand side that looks close to or similar to a lot of stuff on the right-hand side. So more specifically, what I'm suggesting we do is we sort of combine like terms. So what do I mean by like terms? Well, on the left-hand side, I have an x term, and on the right-hand side, I have an x term. On the left-hand side, I have a square term, and I have a square term over here, etc. So every variable from x to x squared to x cubed, every power of our variable shows up on the left and right-hand side. And so what that tells me is that I could combine like terms. So let's do that. in the following way. So what I'm going to look at is the fact that on the left-hand side, I'm going to bring everything from the right-hand side to the left-hand side. So on the left-hand side, I have a c sub 1, but I also have a 6c sub 0 and a plus 9. So I'm going to write it like this. So I'm going to have c sub 1 plus, excuse me, I have to be careful. It's not plus. It's going to be minus because it's coming to the other side. So I have c sub 1 minus 6c sub 0 minus 9. That's my constant term. And then I'm going to have plus what's multiplied by x? Well, what's going to be multiplied by x is 2c2 minus 6c1. And then I'm going to have an x squared term. What's the x squared term? It's going to be 3c3 minus 6c2. Now, of course, this pattern continues forever and ever, but we can at least see what the pattern is. The pattern is as follows. What is the kth term? Well, look at the subscripts, see how they match, and then look at the powers. So if we have our, say, kth power, what are we going to have down here? Well, we're going to have k plus 1, c sub k plus 1, and then it's going to, let me write this a little bigger. That's kind of not planning ahead. So what's happening here? This is going to be k plus 1, c sub k plus 1, minus 6. So notice in each one of these, there's a 6. And then this is c sub k. And then, of course, this pattern goes forever and ever. But we know that that's everything, because then on the right-hand side, we have 0. So what is, okay, so let's take a moment to think about what's happening here, because this is, sometimes this requires a sort of a deep leap of thought for us. Again, I started with an equation, and this equation said that I have some power series equal to some other power series, and they happen to be the derivative of each. One's the derivative of the other, plus some number 9. So what I did is I moved the 6y plus 9 to the other side. And when I do that, I get this last scary looking equation. I have a bunch of stuff plus a bunch of stuff times x, plus a bunch of stuff times x squared, plus a bunch of stuff times x cubed, etc. And that goes on forever, but it has to add up to 0. And not only does it have to add up for 0, it has to add up to 0 for all x. So what does that mean? Well, that means we need all those coefficients to satisfy that whatever's in the parentheses must equal 0. So let's make a note of that. So for the above to be true, here's what we need. Let's do them one at a time. The first thing we need is C1 minus 6C0 minus 9. So we need C1 minus 6C0 minus 9 to be equal to 0. That's the first thing we need. Then we need 2c2 minus 6c1 to be 0. And then we need 3c sub 3 minus 6c sub 2 to be 0. And we need k, or let's do k, well, we could do it either way. Let's do k times c sub k minus 6c sub k minus 1 to be 0. Actually, let me not write out the generic one yet. Let me be a little more clear so we can follow along. I know this is sometimes very overwhelming. So say we're out at like the 100th guy. What's that look like? The 100th guy might look something like 100 c sub 100 minus 6c sub 99 has to be 0. So we need this to happen. So we can summarize all this, and we'll do that on the right-hand side. C sub k plus 1 times the number k plus 1 minus 6 times c sub k. This always has to equal 0. And this has to be true for all k. So what we have is we have sort of a sequence here. We have a sequence, c sub 0, c sub 1, c sub 2. And the beautiful thing about how this sequence is defined is it's defined recursively. If you know c sub 0, you can get c sub 1. And if you know c sub 1, you can get c sub 2. Which means we can compute any one of these numbers c sub k that we want. Does anybody have a question about this so far? I guess we should clean up our sloppy penmanship. Look at this. We're resorting back to my old ways. Okay, so now we got to make use of some things. We have some information that we haven't taken care of yet. So first off, let's note since y, what is y? Remind ourselves of what y is. It's c sub 0 plus c sub 1x plus c sub 2x squared, etc. Since this is the case, y of 0 equaling 2 forces c sub 0 to be equal to 2. So plug 0 in for all the x's, and you get c sub 0 has to be 2. So we can now use this knowledge to determine all the c's. So what was our first line on the previous page? Our first line is c1 minus 6c, 0 minus 9. So if that's equal to 0, what can we determine? Well, if we plug c sub 0 equals 2 in there, we get negative 12 minus 9. So what's 12 and 9? That's 21. So this tells us right away that c sub 1 has to be 21. Again, if I replace c sub 0 with 2, I get negative 12 and negative 9. And so when I take it to the other side, I get positive 21. Similarly, what can we say about these other guys? Well, we can easily take our time to get them. So it's 2c sub 2 minus 6c sub 1. If that equals 0, then that tells us that c sub 2 is, let's write it out more specifically. C sub 2 becomes 6 c sub 1 over 2. Now we can plug that number in if we wanted. We could plug, you know, just for fun, let's plug it in. So this is 6 times 21 over 2. Now notice I'm not computing these numbers yet, because what I'm really looking for is I'm looking for a pattern to make things a little cleaner to write. What was the next guy? The next guy we had was 3 c sub 3 minus 6 c sub 2 equals 0. What can we say about c sub 3? Well, that tells us that c sub 3 is equal to 6c sub 2 over 3. And then what's c sub 2? Well, that is, now watch how I write this, because we're looking for a pattern. If I replace c sub 2 with what it's equal to in terms of c sub 1, well, if this becomes 6 and then 6c sub 1 over 2 all over 3. How can I write this? I can write this as, let's write it as 6 times 6 times c1 over 3 times 2. So let me clean this up. Bye, Ricky. Have fun. What in God's name is happening? Who's getting arrested?
I don't know. The fire trucks have been going all around my neighborhood. I don't know why.
If you get arrested, Daryl, heavens to Betsy. So what we're noticing here is we're noticing a pattern. Does anybody have a question about this? Does anybody think we made any errors so far? Okay. All right, so the first thing that you might ask is, why didn't I just compute these numbers? Well, again, I'm looking for a pattern because I'd like to know what C sub k is. What does it look like in terms of any pattern? Because that's going to be the key thing here. What kind of pattern can I find? Does anybody have a question or a comment right now? Going once, going twice.
So does that mean C sub 3 is less than C sub 2?
What do you mean? Well, it's absolutely gonna. Okay, I won't say absolutely, but that doesn't matter right now. We're not interested in which one's bigger. What we're interested in is what is the pattern. I mean, which one's bigger could be important. It might not be, but what we want is we want a pattern, because we're trying to figure out what function this is, if it is one that we're familiar with. So what we need to do is we need to do whatever we can to get a pattern.
Oh, I'm sorry, no, it's not bigger. Okay. I
It
like
could be, but it doesn't matter.
yeah.
It's just, frankly, it doesn't matter. All right, now before we go on, you know, it would be very bad if we kept going and we have a mistake here. So what we'd like to do is we'd like to double check our arithmetic and our formulas. So if we go back to the previous page, we believe that we need C1 equal to 9 plus 6C0. So if we go back to the very beginning, C1 minus 6C0 grad, yep, minus 9. Okay, so we think that's correct. And then if we plug 2 in for C sub 0, we get the following. So we get 21. When we do this, we get that. Okay, so it looks like we haven't made any errors. And what I'd like to call your attention to is particularly what I am putting my cursor around. The C sub 2 is 6 times the previous coefficient over 2. And then C sub 3 is 6 squared times C1 over 3 times 2. So what we're thinking is that there's a pattern here. What is the pattern that we think we're seeing? Well, let's do the next one. So we know the next one. Let's change colors so it's like a rainbow. The next one, what are we on? We're on C sub 4, right? Yeah, C sub 4. So we have 4C sub 4 minus 6C sub 3 has to equal 0. So that tells us that C sub 4 has to be 6 C sub 3 over 4, if we do the algebra. Now, what is C sub 3? C sub 3, if we plug it in from the previous page, is 6 squared C sub 1. So watch how I write this. It's over 3 factorial. And so now if I do some arithmetic here, this becomes 6 cubed C sub 1 over 4 factorial. Six squared times 6 is 6 cubed, C1. And then if I take 3 factorial and I multiply it by 4, that just becomes 4 factorial. So we've done this a few times, and so what we determine is we think C sub k. Now, what is this, the C sub k? It would be, let's look at this. This would be 6 to the k minus 1 power times C sub 1 all over k factorial. That's the pattern that we've discovered. Does anybody have a question or a comment? So what you should start thinking is something's going on here that looks familiar. These factorials pop up. Let me write that 6 a little prettier, a little cleaner. And then not only do the factorials pop up, which we've seen lots of times, but this coefficient looks very similar to a very familiar function. Does anybody have a question? Okay. So what can we make of this? Well, let's write this down. Here's what we think is happening. We know each of our coefficients, at least we think we know them. And so we think that y is a function of x, and it starts with c0 plus c sub 1x plus c sub 2x squared plus c sub 3x cubed, dot, dot, dot. But we know what these things are. We know that c sub 0, at least we think, is 21. We think we made that correct. And then we think c sub 1 is, if we computed that correct, excuse me, c sub 0 is 2. I'm sorry. So this should be 2. Pardon me, I messed up. So we think this is 2 plus 21x plus, what was our c sub 2? Well, our c sub 2 we found to be 6 c sub 1 over 2, or 6 times 21 over 2. So let's write that in there. And then what did we find our C3 to be? Our C3 was 6 squared times 21 over 3 factorial x cubed. Right, so let's go back to the previous page. Remember, our c sub k was 6 to the k minus 1. So if this was, and then times 21, so 6 The power 2 here, the power 3 here, the power 1 here, the power 2 there. So notice every one of these guys from the second term on has a 21. So let's factor that out. And when I do that, I'm left with x.
Sure, Granny.
Yes.
Is it 3 factorial or 6?
Pardon me?
Is it 3 factorial or 6?
Wait, right here?
Yeah.
It's 3 factorial, which is the same thing as 6, but you want to leave it as factorials because that's the pattern.
Oh,
Like,
okay.
I'll also probably leave this just to be very clear, even though the 2 factorial is 2. Remember the pattern from the previous page. And by the way, I guess I should be a little more clear here, just so this is for k equals 2, 3, 4, etc. That's when this pattern is true. So the c sub k, the kth coefficient, is given by that pattern. And so if I factor 21 out of everything, what I'm left with is this. Now, I am not even, and again, I'm trying to go slow here. So this is 6 squared over 3 factorial times x cubed, etc. And then I say to myself, I say, self, I can do more than this if I wanted, because every one of these guys has an x in it. So why don't I factor that out? Or instead of factoring it out, why don't I get a little creative? Because I guess what I'm saying is, and I sort of haven't pointed out to it yet. What I'm saying is look inside the parentheses. That looks like something. It's not exactly something, but it looks like something that at this point you should know. It looks like the power series for the exponential function. It's not exactly that, but what I can do is the following. I can say, all right, it's not exactly that power series, but if I get creative, I might be able to make it look like an exponential power series. So again, if you're not sure what I'm saying, look, get in your notes, look for the power series for E, and maybe I'll write it up top. So let's give ourselves a hint. So remember, E, let's even beat the dead horse. What is E to the 6x? Well, that's 1 plus 6x, right? Plus 6x quantity squared. Oh boy. 6x quantity squared over 2 factorial plus 6x quantity cubed over 3 factorial. So I almost see e to the 6x down here, but I don't have it yet. So I can get it there if I'm creative enough, though. So that's kind of what I'm trying to allude to. So let's think about how we can do that. Let's erase that and maybe some of our imagination gets stirred. Does anybody have a question? Okay, so how do I get that in there? How do I make those 6s? Notice my 6s are off a little bit. I have the power of 6 is 1 less than the power of x. I need to get a 6 squared, and then I need a 6 cubed, and then I need a 6x. So I want to put a 6 everywhere in there. So how I'm going to do that is the following. what I'm going to do is I am going to watch how I manipulate this. And by the way, let's be very clear. I would never expect you to do this on your own without some help. I'm going to multiply everything by 1. So I'm going to write 21 over 6 out here. And then inside, I'm going to do 6x plus 6x quantity squared over 2 factorial plus 6x quantity cubed over 3 factorial. And what you need to note is this is nothing more than 2 plus 21 over 6 is 7 halves. And what is inside these parentheses? Inside these parentheses is just e to the 6x minus 1. And if you're not sure how I got that, look at the top in the pink. So this is a very advanced argument. This is one that you would probably not think of, but now we showed you it works. And don't fool yourself. Everything I put, we think, well, this is true. This is exactly what the answer is. How do we know? Well, you could differentiate it and plug it in and see it checks, or you can solve using one of the other methods and you'll get the same thing. So what's freaking really cool about this, and by the way, before I say what's cool and then we're going to leave, does anybody have a question?
I have a question.
Yes.
So is ours like e to the 6x minus 1 because we do not have the first term?
That's exactly right. So if you look up in the pink, notice what I did is I took the 1 to the other side. Does that make sense?
Yeah.
Yeah. See, yeah, by the way, this is like, I remember trying to learn this years ago, and I was like, what in the hell is going on? Like, this was mind-boggling to me. But once I went through it, it took me like, I swear to God, it took me like a week to make sense of this. And once I figured it out, I was like, oh my God, this is awesome. Because there's lots of hidden cool crap about this, which I'll explain in a second. But power series turn out to be extremely useful for solving differential equations. So let's just write the final answer on the next page. We can clean this up. So if I distribute to 7 halves, so you have y equals 7 halves e to the 6x. Now, there was the minus 1, right? And then it was plus, let me be very careful. I don't want to spit. It was plus 2. Or excuse me, minus 7 halves and then plus 2. I'm getting ahead of myself. I know the damn answer, that's why. So it's minus 7 halves if I distribute plus 2. And then I can write this in all its beautiful glory, 7 halves e to the 6x. And then what's 2? Well, that's another way of writing that is 4 over 2. So this becomes minus 3 halves. So why do I say there's all kinds of awesome stuff that comes from this? Well, it suggests a very deep thing about differential equations because we could have also solved this the separation of variables. So you could have written this equation. Remember, what is this? This is, we had y prime equals, what did we start with? 6y plus 9, right? So that's the same thing as saying dy times this equals dx. You'll get the same answer. You'll get the same solution. And what that suggests is a very deep fact that is extremely useful in applications. And that is, for certain differential equations, solutions are unique. So it suggests that fact. It also suggests that power series can be used to solve really difficult differential equations. And that's what we do. And these things are used all throughout engineering and physics. And many other places too, by the way. Series are extremely useful. And again, I don't mean to scare you with this example, but it's something you should strive to learn. It's really, once you get through all the scary subscripts and all the letters, it's really not that difficult. It just takes a little, there's a big hump in the beginning. And once you remove that fear factor of all those crazy subscripts, then you can make sense of it. Does anybody have a question? All right, well, I think that's a good place to stop. And I will post all this stuff to the internet. And if I don't hear anything from you guys, have a great weekend. Be safe. Good luck on any finals or anything. And I hope to see you guys Tuesday. We'll answer any questions you have on homework at that time too. All right, everybody, be safe.